In this video, I'm going to show you how to find general solutions of differential equations using separation of variables. So here we want to find the general solution to the differential equation dy dx plus x e to the y equals 0. And the way we're going to do this is we're going to use a three-step process. First, we'll separate, we'll see what that means in a moment, then we'll integrate, and then we'll solve. So the first step, separate. What that means is we want to manipulate this equation so that the dy dx and all of the y terms are on one side, and then all the x terms are on the other side. So let's go ahead and write our equation again. dy dx plus x e to the y equals 0. Why don't we say we want the dy dx and all of the y terms on the left-hand side, and then all the other x terms will go on the right-hand side. So it's kind of like we want to separate the y and the x on different sides of the equal sign. The trick to doing that here is to first move this x e to the y to the other side, subtract it off, and then you get that dy dx equals negative x e to the y. Now we'd like to get this e to the y to the left-hand side and keep this x on the right-hand side. And we can do that by dividing. Now one thing to be careful of whenever you divide is that you need to be cautious whenever you divide by something which could potentially be 0. We're safe here though, because e to the y is never 0, no matter what y is. So divide both sides by e to the y, get 1 over e to the y, times dy dx equals negative x. And there we go. We've got the equations separated. The dy dx and the y terms on the left-hand side, whereas there's only x terms on the right-hand side. Now it's time for step 2, integrate. So we'll go ahead and write down our equation again up here. 1 over e to the y times dy dx is equal to negative x. In this step, we integrate both sides of the equation with respect to x. On this left-hand side, we have both a dy dx and a dx, so we can think of this almost like a change in variables, where the dx's cancel, and then it's just an integral with respect to y. In that case, we've got integral of 1 over e to the y dy equals integral of negative x dx. This right-hand integral is easy to solve, but the left-hand integral requires a bit of manipulation first. Instead of writing 1 over e to the y, let's write this as a single exponent, no fraction, just e to the negative y. So integral of e to negative y dy equals integral of negative x dx. And now we can solve both integrals. Integral of e to the negative y is just negative e to the negative y. So that plus some constant of integration, call it c1, is equal to the integral of negative x dx. That's just negative 1/2 x squared plus a constant of integration, call it c2. And now we're done with the integration step, and it's on to step 3, solve. In step 3, we want to solve for y in our equation. So we'll write it again. Negative e to the negative y plus c1 equals negative 1/2 x squared plus c2. First, let's get this negative e to the y on its own side, all alone. So we'll move that c1 over, we'll subtract it over. So negative e to the negative y is equal to negative 1/2 x squared plus c2 minus c1. Now we can multiply both sides by negative 1 to get rid of that negative in front of the e. So we just have e to the negative y is equal to 1/2 x squared minus c2 plus c1. And for the sake of simplicity, why don't we lump this minus c2 plus c1 into a single constant, c3. The reason we're allowed to do that is, well, c1 is just any constant, c2 just represents any constant, and that means negative of c2 is negative of any constant, which is, well, still any constant. And if you add together any constant and any constant, you still get any constant. So we have that e to the negative y equals 1/2 x squared plus c3 any constant. Now let's get that negative y out of the exponent. So we'll take natural log of both sides. And the result there is negative y equals natural log of 1/2 x squared plus c3. And the finishing touch, just get that negative off of the y, multiply both sides by negative 1, and get y equals negative natural log of 1/2 x squared plus c3. So there we go. There's our solution. Y equals negative natural log of 1/2 x squared plus a constant. Now you might wonder what types of differential equations can be solved using separation of variables. Well, the answer is any differential equation that can be written in the following form. dy dx equals g of x times h of y, where h of y is not equal to 0. It's straightforward to show that we can apply the procedure of separation and integration to solve this differential equation. All we have to do is first divide both sides by h of y. That gives us 1 over h of y. dy dx equals g of x, and we know we are okay to divide by h of y because we assume that h of y is non-zero, and then we just integrate both sides. So we get integral of 1 over h of y dy dx with respect to x is equal to integral of g of x with respect to x. The dx's cancel, and we've just got the integral of 1 over h of y dy equals integral of g of x dx. And then at this point we can just evaluate both integrals and solve for y to find the solution. And because these kinds of differential equations can be solved using separation of variables, we call them separable. Alright, on to another problem. Next up, we want to find the general solution to the differential equation dy dx minus 3x squared y squared equals 3x squared. And to do this, we'll use the same three-step process of separating, integrating, and solving. So first, separate. So write our equation again. dy dx minus 3x squared y squared equals 3x squared. And our goal is to get the dy dx and all the y terms on the left-hand side, and then all the left terms on the right-hand side. Separate the x's and the y's. The trick to doing this is going to be to add this 3x squared y squared to the other side, so that way we can factor out an x term and then divide out by the remaining y term. So we'll add that to both sides, and we get dy dx equals 3x squared plus 3x squared y squared. And we see that we can factor out a 3x squared from both of these terms. So we get dy dx equals 3x squared times 1 plus y squared. And now we divide out by this 1 plus y squared. Again, remember, you should be cautious whenever you're dividing in case it could possibly equal 0, but in this case we're safe. 1 plus y squared is never 0 because y squared can never be negative to cancel out this 1. So divide it, you get 1 over 1 plus y squared dy dx equals 3x squared, and here we go, it's properly separated. We are ready for the integration step. So we'll take the integral of both sides, 1 over 1 plus y squared dy dx with respect to x, that's going to be equal to the integral of 3x squared with respect to x. It's like the dx's cancel, and we've just got the integral of 1 over 1 plus y squared with respect to y equal to the integral of 3x squared dx. And we solve this integral. This is just arctangent of y plus a constant, say c1, that's equal to integral of 3x squared is just x cubed plus a constant, say c2. And lastly, we solve. So let's write this again. Arctangent of y plus c1 equals x cubed plus c2. Let's isolate this arctangent of y term. So arctangent of y equals x cubed plus c2 minus c1, and we can lump these constants together into a single constant, c3, so we'll have that arctangent of y equals x cubed plus c3, and to get rid of this arctangent, we can just take tangent of both sides. So we get y equals tangent of x cubed plus c3. And there we go. There is our final solution. Y equals tangent of x cubed plus a constant. So now we know how to find general solutions of differential equations using separation of variables. These general solutions will always have an arbitrary constant. But in the future, we'll also learn how to find particular solutions of differential equations, in which some initial condition is given, and we have to choose a particular value of the constant, which will satisfy the initial condition.